For the first two lessons of Chapter 7, we learned how to solve system of equations by graphing, by substitution, and by elimination. We're going to learn a new method in this lesson called Gaussian elimination. It's really elimination. Okay? So the first thing that we're going to take a look at is what does it mean for a system to be in row echelon form. So this is a system with three equations and three variables. Do notice the three variables are x, y, and z. And there are three equations. Regular system, a system, an equivalent system, equivalent because the two systems have the same solutions, in row echelon form looks like so. Let's see. The first row has all three variables. The second row only has the variable y and z, while the last row only has the variable z. So this is our goal for this lesson, to take a system that looks like so, where the three variables appear in all three equations, and make it one that looks like a triangle, also known as a triangular system, where the last row contains one variable, the second row two variables, and the first row contains three variables. If you are able to accomplish this, your system now is in row echelon form. Why do you want to put the system in row echelon form? It's easier to solve. The method of solution is called back substitution. So we store the fact, so we're doing example 1 right now, solve the system to the left using back substitution. We store the fact that z is equal to 2. So we already know what z is. It's called back substitution because we're going to work our way backwards. From the third equation, we go to the second equation. We have y plus 3, we replace z by 2. So you have y plus 3 times 2 is equal to 5. Y plus 6 is equal to 5. Subtract 6 from both sides. Y is equal to negative 1. We now know z is 2. We know that y is equal to negative 1. We now go from the second row to the first row. So working backwards. Third row, second row, first row. We have x minus 2, replace y by negative 1, plus 3, replace z by 2, is equal to 9. X plus 2 plus 6 is equal to 9. It's obvious since x plus 8 equals 9. X itself is equal to 1. So we have x equals 1. When we write our solution, we write it as an ordered triple. X goes first, y goes second, z goes last. So 1, then negative 1, and then positive 2. Now remember at the beginning of the lesson we said that this system and this system are equivalent. What does that mean? It means that the two systems have the same solution set. Let's quickly check that that is so. Let's start with the top equation. 1 minus 2 times negative 1 plus 3 times 2 equals 9. 1 plus 2 plus 6 equals 9. Check. Let's move on to the second equation. The opposite of 1 plus 3 times negative 1 is equal to negative 4. Negative 1 plus negative 3 is equal to negative 4. Check. Let's move on to the third equation. 2 times 1 minus 5 times negative 1 plus 5 times 2 is equal to 17. 2 plus 5 plus 10 is equal to 17. Notice that our order triple satisfies all three equations, so it is a solution of this system, but also of this system. When two systems have the same solution set, the two systems are equivalent. What we're going to do now, we're going to talk about the operations that you can use to obtain equivalent systems. So here's what you can do. You can interchange two rows and the two systems are still equivalent. You can multiply one of the rows but by a non-zero constant. And then you can add a multiple of a row to another row. So we're going to zoom in our book so we can see those operations. They're right here. I'm not going to write them on the board. There they are, exactly as I described them. And now we're going to do an example. Example 2, using Gaussian elimination to solve a system. So our goal is to use Gaussian elimination to solve a system. Yes, I know I'm going to make it more cumbersome than it needs to be. But what is this? This is a preview of what is coming up in Chapter 8. We're going to learn how to use matrices to solve systems of equations. So my first step, yes, I know it's totally unnecessary. We write something like this. What does this mean? It just means we're going to interchange row 1 with row 2. Why would we do something like that? Well, we do something like that because when we get to matrices, you'll see that we always want a variable with a coefficient of 1 in the first row, first column. So yeah, x minus y is equal to 0, and we have 3x minus 2y is equal to -1. Now, my goal is to put this in row echelon form, so what I want to do is get rid of the x's from the second row. So I'm going to write row 2 plus -3 row 1 is the new row 2. So notice, this is 3x. If I take the first row and multiply it by -3, I'm going to get -3x. So row 2, this is row 2, 3x minus 2y equals -1. Row 2 plus -3 row 1. Take row 1 and multiply everything by -3. Everything on both sides. We get -3x plus 3y is equal to 0. Add them together. This is going to be your new row 2. What do we get? 0x plus 1y is equal to -1. Rewrite your system. Let me erase all of this, unnecessary. We did not touch the first row. So the first row is x minus y is equal to 0. We did touch the second row. The second row is now row 2 plus -3 row 1. So here is row 2 plus -3 row 1. 0x plus 1y is equal to -1. Or just y is equal to -1. Now, the system is in row echelon form. I can now use back substitution. We're going to use back substitution. So we're going to go from row 2 back to row 1. So we're going to have x minus -1 is equal to 0. X plus 1 is equal to 0. X equals -1. -1 is our solution point. Quickly check mentally. check negative 3 minus 2 times negative 1. So negative 3 plus 2 equals negative 1. True. Negative 1 plus 1 equals 0. Also true. The point satisfies both equations in the system. It means we were successful in solving this system.